Okay, welcome back. Can we start again, please? Okay, so remember that what I've discussed in the first half of the lecture was that instead of just having a sort of random order in the fringe and then using them either as a queue or as a stack, we can now also apply an ordered queue, and the way to order them is the best, of course, if we know the distance from the goal state. But in obviously in all serious search situations, we don't know that, so we need this sort of approach via heuristics, rules of thumb. And the definition or the notion of the best first search algorithm is that you have this ordered list and you always take the first one out of it and evaluate it. And there is one notion is that one of the greedy best first search, and that one always is in a relatively naive way, always takes in the exploration to build up your search tree, the one that is the closest to the goal according to some heuristics that you're using. Yeah, we are going to see an extension of this, which is a bit more smart, and that is then the family of the A algorithms. So let's start with the more naive one, which is the greedy best first search. And that basically is that we take the heuristic value, in this case the beeline distance that we have from a city in Romania to Bucharest. That is now our best state to evaluate in our fringe, and that gives us the search algorithm. So let's see how that works. We have here a list of distances, and you have to trust me that those values that I will use in the search, they come out of this table. I just look them up, and they are basically all the distances from all these cities in this map to Bucharest. So the goal is to go from Arad to Bucharest, and the only thing we know about it is that we have a beeline distance between Arad and Bucharest of 366 kilometers. Yeah, so that's the first element. That's our starting state. That's what we put in the fringe, and then of course we take it out again because we only have one element. We take it out again, and we look at all the possible places where we can go from Arad. And in this drawing, which you can look up later, there is the option of going to Zerind, Sibiu, and Timiascu. Yeah. So basically, this is what we're now going to explore, namely the distances that we have from Sibiu to Bucharest, from Timișoara to Bucharest, and from Zerind to Bucharest. And again, the only thing we do is we look at the beeline distance between those possible new successor states and Bucharest, and we take in the greedy way, we order them, and we start from the top one in the list, the best one, and continue our search there. Yeah. So this is the expansion procedure, our three options, and the greedy best first search algorithm will choose CBU. So now we look up in the map again, which are the places where I can go from CBU, and then I get Arad, I get Făgăraș, I get Oradea, and Râmnicu Vâlcea. These are just the places where I can go from CBU according to the map. And again, I just look at now all the states that I have in my list, and these includes those two. Arad, Făgăraș, which has the shortest distance according to the straight line distance to Bucharest, and I choose in a greedy way, I choose this one to pursue. In other words, I keep the order in my list, but I only take the best one to start with. And the only thing that influences the choice is the heuristic itself. So then the next one will simply choose Făgăraș. I can now go back to CVU, or I can go to Bucharest. And that basically allows me to find a path between Arad and Bucharest. But if you do the maths, you will see that this is not the optimal one. It's not the shortest path between Arad and Bucharest. Yeah? So it finds a solution, but it doesn't find the optimal one. Because the optimal one would be this one, Arad, Sibiu, Râmnicu, Vilea, and Pitești. But where does it go wrong? It goes wrong here, namely that we think Făgăraș is better because it is more direct to Bucharest. But if we would take this detour, we would get to Bucharest faster. Okay. So we find a solution, but we don't find the optimal solution. And it's not even complete. So it could happen that if we start here and we take our heuristics, that we just put Neamt in our list, and then there is nothing better, so our search would stop. Yeah? So we have an algorithm that takes these heuristics into account, and that works reasonably efficient. But the danger is that we don't find an optimal solution and that we don't find a solution at all. So one thing you have to do is, in order to avoid those infinite circles, because what could happen, for example, is that we go to always to a shorter one and then back again. So in principle, I said you wouldn't go back, which is not true. You would go back because this one is then the next one. You only have one successor. You would go back, but then the next in the greedy search would again be named. So you would end up in an infinite loop again. That's obviously not what you want. So you can stop that by repeating states and keep more things in memory. But this is, in principle, the original algorithm is not complete. So the idea was in the greedy algorithm that you always take all the nodes and keep them in memory. So that is, if we go back to this example, that's what I said. Okay, those are still in the fringe, even though they have no values, so they will be at the end of the queue, but they would still be in the fringe. So that's quite memory intensive still. So what people do, what you can do, is to say I restrict my fringe only to a certain number of states. 5 states, 10 states. I always keep the top n ones in memory. And that basically reduces your memory problem. So we don't have to have an exponential number of states in the memory anymore. But of course, now you're not optimal anymore and not even complete. Yeah? So the idea of restricting the size of the open list, the fringe, is called beam search. Because basically what you do is that you have this complete tree that you would otherwise have to explore, but now you don't explore the whole full breadth of the tree, but you always only have a restricted number of these n states. So basically your search space looks like a beam that goes through your tree. So this is a variant that helps you deal with the memory inefficiency or the memory problem of best first search. It's called beam search. Restrict your memory size and do that by restricting the size of the fringe. There is a sort of the most radical way of doing that, and that's called hill climbing. Hill climbing has a strategy of a beam of size 1. So it only takes the optimal one and throws away everything else. So if you have greedy best first search with only one element in the fringe, then that's called hill climbing. And hill climbing has many, many advantages. namely that it is extremely fast, it is extremely memory efficient, but as you might have guessed, it has big disadvantages, namely that you do not find the optimal solution necessarily, and that you might not find a solution at all. And then again, the question, of course, according to the choice of your best, the one best state that you pursue your search is really depending on your heuristics. Why is it called hill climbing? And that's the visual metaphor that if you see your search space and you have your heuristic values, then what this is very often compared with is this sort of landscape where you have an optimal solution maybe here, and the hill climbing is always trying to find a better solution. So if you're somewhere here in your search space, you have a heuristic value, then the hill climbing algorithm will always go up, go up, go up, will always try to improve this one value until you end up on a hill. But this is then a local optimum and not necessarily the solution which can be higher. And if you end up here, you will actually never find the solution unless you really by coincidence end up on this specific part of the search space where your solution is in. That's where the name hill climbing comes from. So if we go to the example of the traveling in Romania, then basically you expand all the nodes, you look at all the nodes in that you could reach from Arad, you take the best one, the closest one, and then you throw the other two simply out of your memory. You don't have them in the fringe anymore. You do the same with CPU. You look at the other three, you take the best one, you forget about the other ones, and then you reach Bucharest, as you would have done with the greedy search, but in this case, far more efficiently. But this obviously helps you end up in weird places of Romania very effectively if you have the wrong heuristics chosen or if you're just unlucky. Because if you one time move in the wrong direction, you are simply doomed and you're lost. So all these algorithms we have seen so far, they work, they help improve over the naive, uninformed search, but they are not still not good enough for practice. And what the difference now is this family of A algorithms, as I called A and A star, and that is that we're not only looking at the heuristics as our estimation from how far we're still away from the goal, but also how much have we already paid to get into the state where we are now. Yeah? So the BestFirst search is now not only evaluating this evaluation function does not consist only now of the heuristics, the distance between the state where I am to the goal, but it also takes into account the way that I have taken from my starting point. So it's the best known form of best search, and it's not greedy because it not only tries to get to the goal as quickly as possible, but it also tries to take into account the path that I have already taken. So the evaluation function f, with which I order the fringe, now consists of the part g, which is the cost so far to reach the node where I am in, plus the costs of the estimated cost to get from the node to the goal. And f of n is just the sum of the two, and in that way it's the estimated total cost of the path from the starting point to the goal. And then through the node, the specific node where I'm in. So when you get the task of calculating with an A algorithm, then this is all you have to do. You have to calculate the value of f of n by the sum of the g of n, which is the path from the goal, and the h of n, which is the path to the goal from the node. And for the age, you obviously use one of the heuristics that we've been talking about before. And now if this heuristic has a specific property, and that's the property of admissibility, then this algorithm is called A star. So it has is a specific instance of the algorithm A with the condition that A has an admissible heuristics to estimate the distance from the node where I am to the goal. And what does this heuristics being admissible mean? It means that the heuristics never overestimates the goal, the distance, sorry, the costs to reach the goal. Oh, what's happening here? Sorry, pressed too many buttons at the same. Okay. To start the recording again.